students, today we are going to learn how to derive the one-dimensional heat equation. Before starting the derivation, let me know first what are the three empirical laws we are going to use in deriving the heat flows. The first one is heat flows from higher temperature to lower temperature. The second empirical law is the amount of heat in the body is proportional to mass and temperature. The third one is the rate of heat flow across area is proportional to the area and temperature gradient normal to the area. These three are the empirical laws we are going to use in deriving the one-dimensional heat equation, which you have already studied in your physics. Now, we'll move on to the derivation. To derive this, first of all, let me consider a homogeneous bar of constant cross-sectional area A. This is the constant cross-sectional area A. This is the homogeneous bar. This A, the slab, is, what is the distance of the slab? Delta x. If x is the distance from the origin to the slab is x and delta x is the thickness of the slab, then the end of the slab is at a distance x plus delta x from the origin. I repeat once again, if this is the homogeneous bar of a small cross-sectional area A, this is the area A, with the thickness delta x is the thickness, and x is nothing but distance from the origin to the slab, then the end of the slab will be at a distance x plus delta x from the origin. Ri is the rate of heat inflow to the slab. Ro is the rate of outflow of the slab. Ri, inflow, means you will be getting negative sign. Ro, you will be getting positive sign. This is the descriptions about the diagram. Now we'll move on to the derivation. I am going to consider a dependent variable and two independent variable. Let u is equal to u of x comma t be the temperature of the slab A at a distance x from the origin. Here u is the dependent variable, x and t are the independent variable. So when we are differentiating u with respect to x, you will be getting dou u by dou x, first order. Second order derivative of u with respect to x, you will be getting dou square u by dou x square, and derivative of u with respect to t is called dou u by dou t, because u is a function of two variable x and t. Now, if u is temperature of the slab, then delta u be the change in temperature of the slab with the thickness delta x. Let rho be the density and S be the specific heat. What is the definition of rho? You have studied rho means mass per unit length. You have studied in your physics. Rho, the density is mass per unit length. And what is S, the specific heat, is the amount of heat required. Okay. Yes, rho, the density definition is mass per unit length. Yes, the specific heat, what is the definition? Amount of heat required. Now, from rho is equal to mass per unit length, I can write the mass of the element is A rho delta x. A is the cross-sectional area, rho is the density, delta x is the unit length, the thickness. Correct? Because from the definition of density, mass and unit length, we can write mass is density into unit length. That's what we have got, A rho delta x. Now, the quantity of heat stored in this slab element is, what is the definition of this? Using the second law of empirical law of heat flows, I am writing. What is that? The second law of heat flows. The amount of heat in the body is proportional to mass and temperature. The amount of heat in the body is proportional to mass and temperature. That's what we have written. The quantity of heat stored in this slab element is mass into temperature. What is mass? From this line, I have written mass is A rho delta x. And temperature, here delta U is the change in temperature, S is the specific heat. Both I am writing S into delta U. Okay. This is quantity of heat. What is the rate of increase of heat in the slab? We have to differentiate this with respect to T. Hence, the rate of increase of the heat in the slab element is given by R is equal to A rho delta X S dou U by dou T. That is, we have to differentiate this equation with respect to T. Here, U is the only dependent variable with respect to T, means delta U with respect to T is dou U by dou T, because partial derivative. U is a function of two variable X and T, which I am keeping it as equation number 1. Now, if Ra is the rate of inflow of heat and Ro is the rate of outflow of heat, using Fourier law of heat conduction, what we'll get? I'm moving on to the next. Here, see that Ri is inflow. Ri is inflow and Ro is outflow. Ri you will be getting negative, Ro you will be getting positive. So using this, using the Fourier law of heat conduction. What is Fourier law of heat conduction? The rate of heat transfer through a material is proportional to the negative gradient in the temperature and to the area. That is area. That is the Fourier law of heat conduction. Using the Fourier law of heat conduction, we have got Ri is equal to minus Ka into dou U by dou X at X, because Ri is inflow up to the slab at the point X. Ro is nothing but Ka into dou U by dou X at X plus delta X, because it's outflow at the point X plus delta X. Why this negative and positive sign have written in the diagram, the figure? This is outside means negative, inside means this one is negative and this is positive. This, the Ri and Ro both together, I am keeping it as equation number 2, where K is called the thermal conductivity. K, the constant, is called the thermal conductivity. Now, from equation 1 and 2, we have got R is equal to Ri plus Ro using the law of conservation of energy. What is law of conservation of energy? The energy can neither be created nor destroyed, only converted from one form of energy to another. Using this, we have got R is equal to Ri plus Ro. Now, I am going to substitute the value of R from equation 1. Ri and Ro from equation number 2, I am substituting. I have got this line. What is that? A rho S delta X dou U by dou T is equal to minus Ka dou U by dou X at X plus Ka dou U by dou X at X plus delta X. Now, from this line, I am taking, apart from this dou U by dou T, whatever the other term we have got, everything I am going to bring it to the denominator of this RHS. So, what you will get the next line? Dou U by dou T is equal to, the positive term have written first, negative term second, by taking the common part, that is Ka outside. Ka into dou U by dou X at X plus delta X minus dou U by dou X at X divided by A rho S delta X. Okay. Now, this A and this A, numerator A and denominator A, you can cancel it. What will you get? K by rho S of dou U by dou X at X plus delta X minus dou U by dou X at X divided by delta X. By taking the limit delta X tends to 0, both the sides, what will you get? Limit delta X tends to 0 of dou U by dou T is equal to limit delta X tends to 0 of the other side. But K by rho S is a constant which is independent of this delta X. So I am writing first K by rho S of limit delta X tends to 0 of this derivative. Dou U by dou X at X plus delta X minus dou U by dou X at X divided by delta X. What is this? This is the derivative of dou U by dou X. Because the partial derivative definition, we know that as dou U by dou X means limit delta X tends to 0 of U of X plus delta X minus U of X divided by delta X. Here, dou u by dou x at x plus delta x minus dou u by dou x at x divided by delta x, when delta x tends to 0, will be the derivative of dou u by dou x. That is dou by dou x of dou u by dou x, that is dou square u by dou x square. Now, when we take k by rho s is c square, where the constant c square is called the diffusivity. Hence, we obtained the one-dimensional heat equation derivation. Thank you.